That's hard.
How are you?
Okay. Okay, thanks, Subir. So the title of my talk today is Transport and Chaos in Lattice SYK models. So this is a work in collaboration with Yingfei and Subir. So because of time limit, I will focus more on the interesting part, which is the chaos story. So let's do a short introduction of quantum chaos. So quantum chaos has its classical origin, which is called the butterfly effect. It basically means that if you perturb your initial condition a little bit, the error you get in the later time actually scales exponentially with time. And this exponent is defined as the Lyapunov exponent. And in quantum mechanics, there is also a proxy for diagonalizing this chaotic behavior, which is the so-called out-of-time order correlator. So there are two ways to write this correlator. The first way is to write it as the commutator of two local operators and then square it. And then equivalently, you can actually expand this commutator and then write it in this kind of out-of-time order form. And then the schematically behavior of this commutator square is that at the early time it's basically zero because there are two local operators and you have locality. So these two operators actually commute. And then at a later time, because of interactions and scrambling, this O-talk will grow exponentially in time, and then at a later time it will saturate to some constant value. A more interesting question to ask is how does the chaos actually propagates? So because we know that the O-talk is kind of encodes the information about like how quantum entanglement or scrambling propagates in the system. So there are two famous bounds for this quantity O-talk. So the first bound is called the Lieb-Robinson bound. It's basically saying that in the local quantum system, the O-talk satisfies the following inequality. So first, for temporal growth, the growth cannot be faster than an exponential rate, and then for spatial propagation, there is actually a velocity limit at which you can propagate, which is called the butterfly velocity. And the second bound is proposed by Maldacena, Shanker, and Stanford. It's basically the fundamental bound for chaos. That the Lyapunov exponent lambda L is smaller than some fundamental constants times 2 pi t, and this bound is actually saturated by some systems like black holes and the SYK model. And when people actually go to compute this O-talk for some particular systems, they actually find different kind of behaviors. For example, in some weakly coupling systems, for example, in Fermi liquids or some like weakly interacting OM models, they actually find that the O-talk actually looks diffusive. The meaning is that the O-talk looks like the solution to some kind of diffusion equation. And in some other systems, for example, some strongly interacting systems like gravitational systems or SYK models, the people found that the Lieb-Robinson bound is actually saturated, and there is a well-defined butterfly velocity VB. And moreover, there is a interesting connection between the chaos propagation in this strong coupling case to energy transport. To compare this thing to energy transport, we can actually engineer those butterfly velocity VB and the Lyapunov exponent lambda L into some quantity that has the dimensionality of a diffusion constant like this. And people also computed the energy diffusion constant, and they found that up to some order 1 factor, they actually scale the same way. So people have been conjecturing that these two quantities are somewhat the same. But there is still this controversy that whether the O-talk actually is diffusive or has a well-defined light cone, because the conventional approaches for computing those O-talks are usually like, for example, summing over round diagrams or doing best arbitrary equations, and these equations are very good at determining the Lyapunov exponent lambda L, but however, the spatial propagation structure of the O-talk is actually controlled by the prefactor of the exponential growth, which is CQ. And then it's really hard to find this prefactor in this best arbitrary equation approach. So in this talk, I will propose I will try to use some new tool that's developed by Yingfei Gu and Alexei Kitaev that actually reveals some analytical structure about the prefactor of the O-talk, and it enables us to actually compute the spatial profile of the O-talk. So this tool is called what's called a ladder identity. So the assumption is that when you compute your O-talk, you do it by summing over some ladder diagrams or round diagrams, and their result is that if you do this kind of summation, there are some self-consistency relations that must be satisfied by those diagrams, and the outcome is that the O-talk will actually have a pole in momentum in its prefactor. And this pole is defined such that when in momentum space, such that you treat the Lyapunov exponent lambda L as a function of momentum Q, and you will find that at some value of Q, this lambda L will hit its maximal value 2 pi t, and the pole is exactly sitting at this place. And having known about the existence of this pole, we can actually go out and compute how the O-talk propagates in space. The way you do this is basically you Fourier transform from momentum space to real space. It's basically some Fourier transform looks like this. Then the conventional way we do this kind of Fourier transform is to assume that the space-time distance are really large. For example, x and t are large. So you can actually evaluate this integral by saddle point. So of course there's a first contribution to this integral, which is the saddle point contribution sitting at q star. But when you deform your integration contour to pass the saddle point, you may or may not hit the pole. So if the pole is hit during this deformation process, then you also need to include the pole contribution, which we define here as Q1. So the result of this analysis is the following. So first, I can consider you are in some strongly interacting system that the scrambling is fast, such that the Lyapunov exponent lambda L is actually close to 2 pi t. So in that case, this diagram is the space-time profile for your O-talk. So there are two boring regions C and D. In region C means that the O-talk is still small; it hasn't started growing yet. But in region D, the O-talk has already saturated. So this is the region A here is actually the short distance region is actually dominated by the saddle point. And then the outcome of the analysis that the O-talk is actually diffusive. But if you move over to region B, the pole is actually getting hit during the deformation, and then you actually need to include the pole contribution, and the pole contribution actually dominates. So there are two interesting features of the result that's dominated by the pole. So first, there is a well-defined butterfly velocity VB, which can be determined from the position of the pole. And the second feature is that the Lyapunov exponent in that region is actually comes out to be maximal. And there is another less interesting limit is when your system is weakly interacting, and then your Lyapunov exponent lambda L0 is actually small. And in that case, there's no chance that you will hit the pole during the deformation, and then the whole O-talk is actually diffusive over the whole space-time. So next, I will try to apply this result to a lattice SYK model and see what kind of new results we can get. So the lattice SYK model that we are considering is the same model that's proposed by Xiuyang Song, Chang Mingjian, and Leon Balance. So it's a model of SYK islands plus a hopping turn. At each side of the lattice, you got an island of SYK model where there are many electrons that can interact through this SYK random interaction. And also, between the neighboring lattice sites, there is a random hopping turn Tij, whose mean value is actually T naught, such that the electrons can move back and forth between different sites. And you can write down the Schwinger-Dyson equation for such a system. And the new term you get from the original SYK model is this new T naught squared times Gx term. If you do a scaling analysis for this term, you will find that it's actually relevant at low energy. That means that there is actually a different physics at low energy. And it turns out that the new physics is actually a heavy Fermi liquid. So there is a coherent energy scale EC, which is defined to be T naught squared over U. And below this energy scale, the system behaves like a heavy firm liquid, the physics actually dominated by this T0 square term. And then at the high energy side, when the system becomes an incoherent metal, and the physics is actually dominated by SYK model. So in the original paper by Leon Balance et al., they have computed the transport properties of that model, and they see that there is a nice crossover for those transport coefficients, where at the low temperature they see a t squared growth of the resistivity, and it becomes a linear in t relation at higher temperatures. And our new contribution to this model is that we computed the chaotic properties of that model, that we actually look at the Lyapunov exponents lambda L's, and how the chaos and how the OTOG propagates. So for the Lyapunov exponent lambda L, what we found is the following: it's consistent with the heavy firm liquid to SYK crossover picture. So at low temperature, we found that the lambda L is scale as a t squared or EC, which is basically a signature of some firm liquid like a scattering mechanism. And at the higher temperatures, we found that the Lyapunov exponent is actually saturates to the maximal value. And using the ladder identity, we can also compute how the OTOG propagates in space. And we found that there are two kinds of diffusion constants. A short distance diffusion constant d star and a long distance diffusion constant d chaos. So this d chaos is not a real diffusion constant. It's just some property we made out of the butterfly velocity. And what we found is that the fake diffusion constant d chaos is actually quite has kind of a similar behavior as the energy diffusion constant dE that we computed from Kubo formulas. And we found that at short distance, the short distance diffusion constant d star has a totally different behavior. So our findings again confirms the conjecture that the energy transport and the scrambling are somehow related. So to summarize our findings, we actually found that at the low energy, we found that the OTOG is totally diffusive, but at higher temperatures, the OTOG actually shows a well-defined butterfly velocity. Okay, that's all for my talk. Any questions?